to recording. Hopefully nothing happened and we are okay for that recording. So this is 12.3, and what I want to do is just really quickly recap one of the concepts that I have had. Okay, perfect. Thank you, Peter. Then we can just continue. You see, if you have had any type of integration, the first thing and the main thing and the most important part to just compute your integral is your limits of integration, okay? So all we have done last time was type 1, type 2, and that's just really try to select the one which is easier for computation. And the problem is when we have just something like a circle, then calculation will be harder. So let's say my region of integration looks like this. So that's just really how I want to practice what we have done in, let me just make some room on right side. So what we have done in last class, so it's just if this was the region of integration right over here, and you're supposed to do either in type 1 and type 2, so you just say, okay, this is the minimum value of the x, which is -1 because the radius is 1, and this is the maximum value. So then that would be just really starting from -1, ending by 1 when you have the dx. And then for writing the dy, you are moving along the y-axis. You just say, this is the first thing that I hit, and this is the last thing that I hit. And since this is just really y, I have to solve this equation from y, so that would be like this. So you just move with the x squared at the other side. Is the square root of plus minus the square root of 1 minus x squared. So that means I have always two pieces of the circle. The bottom piece is negative because it's under the x-axis, and the top piece is positive because it's above the x-axis, okay? So according to what I made over here, so let me make it. What I have had over here, it was just really beginning from here, ending here, right? So it's always from this bottom piece of the circle to the top piece of the circle, and that gives you really the limits of integration. So that means you have to go from here to here. So that the problem, this is for dy, and then if you have something to integrate, you just really put it inside. But the problem is for this type of integration, since you have this what is radical notation, you do need to have your trig substitution method, which is just really hard. Usually we just say we don't need to make that much complicated integration, okay? So that's why we just say, okay, do we have any easier way to set the limits of integration for such this problem which having square roots like these circles? Then that's a polar system. Just to practice for this problem, at least I can say whenever I have a polar system, this is just going to be like a unit circle exactly, and this is going to be beginning of the angles, so that is covering the entire unit circle. So it goes from exactly 0 to 2 pi to cover entire circle for the angle, and for the radius, as you see, is just really right over here, because the radius of your circle is 0 to 1. So instead of having these radicals and then trig substitution for integration, I can easily say this is just really two constants and integration is easier, okay? So that would be just really equal, if I just write this by polar is from 0 to 2 pi for angles, and then from 0 to 1 for the radius. But the problem is, it's not really direct like that. I need to just take care of something else right over here. When I'm doing that change of variable, is like u substitution, which you have a du. So you are changing really your variable from dx dy to the dr d theta. So then I have to learn, okay, so what's that extra factor that I need to put over there? So, but obviously that makes my job easier. By this way, I have had really all of these limits of integration constants. When this is a constant, means just really rectangular region means what I like. Even for the right side one, for the right side one, if I want to practice, I'm not going because that's just really tough. If I want to practice how will be the limits of integration, so this arrows that I'm just making with this green is going to be for the y direction or the limits of the y. Do you see? First, I have started from the line of the x-axis, and then I end up with that circle equation. And then if I just move on this line, which is a line of x equals 1, then my limits of integration will be different, because this piece is starting from this circle ending by this circle. So that's my second piece. And then if I just move more to this line, which is what is x equals, sorry, that was x equals -1, and this is x equals 1. So that just really changes to limits of integration to be completely different, because this time I'm using from here and then I'm ending by the circle of this one, okay? So that means if I supposed to do by at least type 1, I have to just make it to 3 pieces, and same for type 2, we have to do it with 3 pieces. 3 pieces because these lines will change the limits of integration, okay? So you do have one piece here, and then 2 pieces on right side and left side, okay? So but if you use just your what we call polar system, what we call polar coordinate system, that's just really all constants, because all we have is just really starting from the theta equals 0 and then go all the way to the pi, and that gives you the constant, which is fine for integration. I don't need anything like just trig substitution or hard techniques that we have learned in calculus 2 to integrate. And then for what is it, for the other one, which is the radius, is just clear. The radius start from right over here, which is 1, and end by right over here, which is 2. So this is just simply integration from 0 to pi for the angles, and it goes from what is it, 1 to 2 for the r, and then I have something to take care of that. So what's the goal? To learn how do we set the limits of integration in polar if the region of integration is something like a circle, because in that way it's just really a lot easier. Make sense by now?
Yes. Or I have a quick question for you.
Mm-hmm.
So when we're changing it to polar coordinates, when we add the dr, are we supposed to add the r before the dr?
What was it?
Are we supposed to add another r before the dr?
Yeah,
When we...
that's just what I put as question mark. Exactly.
Okay, cool.
Exactly. So that's just the question mark. So what happened if you're changing your variable from the XY coordinate system to the polar system? You have to pay for that, and your payment is that extra factor of the r. Exactly.
Okay, sounds good.
Yeah. So this is just really to remind you what we know and what we need here for the polar system. So the polar system, I mean, we have learned in calculus 2 somehow, but that's the entire part that I will need from that calculus 2. What it is, you just need to know, if I give you something in XY coordinate system, and then you're supposed to write it in the polar system, so then that would be r square is x squared plus y squared, and then that would be theta equals tan inverse of y divided by x. And then if I give you something in polar system and you're supposed to move it to the xy system, x is r cosine and then y is r sine, okay? So I know we have learned a lot of stuff in calculus 2 for this type of polar system, like graphing thing, but for now I just need to know these 4 formulas, how to transfer from polar to the rectangular and how to move from rectangular to the polar system, okay? So I need this much of here. And this next slide is just really remind you, as any type of integration, if I want to start to define the integration, I have to chop it to the pieces, and then out of those pieces pick a lucky point, and then try to make the what we call Riemann sum, and that's just really any new type of integration. So if you want to define your integration in calculus 1, you have done the same thing. You just make it to the pieces and then pick a point and then make a Riemann sum. Then you define your single integral. And here in 12.1, we have done the same thing to just define what we call integral. So as we know, we have several types of integration in this section, this chapter and next chapter. So the process is going to be always the same thing. So this is a given region for me. So what it is, you have all numbers, all constants, right? So you just have this, it's a constant, this is a constant. So this is just really telling me that the angle of this region between two numbers looks like this, right? So the angle between two constants is just like this, like your rectangular region. If you want to say it's between two constants, they looks like this. So this is your lines in calculus, in rectangular coordinate system. So this is just the lines in rectangular coordinate system. But in polar coordinate system, your lines or your constant looks like just the angles are constant, looks like this. And then if the radius is constant, why it doesn't work? Okay, so when the radius is constant, so means you are between two circles. So this is circle number 1 and this is circle number 2. So this is when your radius is constant between A and B. So means you are moving from the circle with the radius of A to the circle with the radius of the B. And then if your angles are constant, so means you are moving between these two lines which is starting from the origin. Okay, so this is my rectangular region in polar, and what's the goal? Chop it to the pieces, pick a point and make a Riemann sum to make it in polar system. Okay, so chop it in the R direction to the pieces. So you just have the radius is moving from A to B, and you make it in the pieces, which the size of the pieces is always end point B minus the start point A divided by how many pieces you have done. And same thing for the theta direction. So you just have to say the entire limits is from the alpha to beta, you chop it to the pieces, and then how will be the size of the pieces, end point minus the start point divided by number of pieces. So that was just really similar to what we have done. What happened for region of integration? This is what happened. When you make it to the pieces, your pieces is not really perfect rectangle or perfect square, right? So they look like just something. If I make it bigger, they look like something like this. If I just say this is my ith piece, so it's not perfect. It's not perfect rectangle or square to just say I have had delta r and then I have had delta theta. So then the area of this region is going to be directly delta r times delta theta. It is not. As we see, this is not, because this is not a perfect rectangle, right? So that extra factor that I think Ken asked me is just really to make that thing possible, right? So this extra factor, because is making this one really like a straight rectangle and just possible to do that area, is just really the extra factor. The geometric reason for that extra factor is right over here. If you are math major, you need to know that geometric reason, but if you're not math major, you're fine. Okay, so all I need to know is the area of this region from geometry. To find the area of this region is not directly multiply delta r to delta theta, because that's not a perfect rectangle or a square. So then it's going to be, if I can make a bigger graph, it's going to be the sector like this, the area of sector from geometry like this, and minus, if I can just make something more clear, so I just say purple probably, so minus this area. Okay, So from the geometry, if I need to get the area of this little piece right over here, so this little piece right over here, I have to just subtract the big green sector area minus the small pink sector area. So that gives me that little blue piece, okay? So that's calculation. And then again, I told you, if you're engineer, you don't need to know, but if you're math major, you need to know this part. So since the area of sector was half of r square theta when we have a central angle, so that gives you the calculation to be like that. So the area that I was looking is just going to be the area of large sector minus the area of small, as I showed you in the graph. I'm going to go back and one more time to see what do I mean. The green one was the large one, and the pink one is the small one. Subtraction gives you that blue region area, or just the section, the sub pieces area that you need. So that's just really a little bit geometry here, because area of the sector is half of r squared theta central angle. And then when you do that calculation, is by algebra, difference of squares, and then you can separate it, and that gives you that extra factor because of this r right over here. So it's coming from just really what we call area of the sector, what we call geometric reason, because we have algebraic reason at this last section of this chapter. This is just the geometric reason. So entirely, if I want to wrap up for calculation, it says whenever you have these pieces, you pick a lucky point. So then you have to write everything in terms of the polar. What do I mean? X is r cosine, y is r sine. And then you have to multiply that by the sub pieces area. What's the sub pieces area? Is not exactly delta r and delta theta. It has extra factor for that geometric reason. And then you let the number of pieces to be more and more and more. And that's just what we call integration in polar system. So integration in polar system is when you make the number of pieces to be more and more, and then when you change the delta a to be delta r and delta theta, and then you will have that extra factor of r right over here. So if I want to say what's the formula I need to know from here, is just really this whole thing. I can just make any dx dy to be dr d theta if you transfer or convert every single xy to the polar system by the formulas that we know from calculus 1, and if you keep that extra factor of the r for every single integration. So then if I go back to the top thing that I have started, I have to just remember it was possible to do in both coordinate system. But if I am doing in this coordinate system, I don't know which color is more clear. So I have to always add one r over here. I have to always add one r over here. So it's not really dx dy to be exactly dr d theta. It has extra factor of r for that geometric reason. Is there any question?
So we're multiplying that extra factor of r?
Yes.
Okay.
And this is the geometric reason behind of that. Is there any question? If you write anything on the chat, if the page is maximized, I don't see. Okay, so nothing there. Okay. So let's just practice with the problem, like just really from the blank. When I say from the blank, because it's just really graphic, right? So we have practiced many graphs. So this is just really the place that I'm using those graphs to set the limits of integration. This is just ask us to evaluate something. How do I know? That's a lot easier to go by polar than XY coordinate.
Because it's a circle?
Yes. This circles number 1, and this integrand number 2. Because when you have 16 minus x squared minus y square. So that is basically 16 minus r square, right? So that's a lot easier to integrate if you are having in x squared plus y squared to be r squared by formula of the radius in polar, and then for just having that circle region, okay? For that circle region, if I just set the limits of integration, based on that, I need to make the circle, if it says upper half plane, so that's why I'm just making half of the circle, then I don't need to erase the extra piece. So this is from radius of the 1 to the radius of the 2. This is from radius of the 1 to the radius of the 2. That's just going to be the region of integration, or the one that you need to set the limits of integration, right? And I will say 90% of the time we will start with the theta in this course. And it does have type 1 or type 2 here. Means you can start with the theta to be constant or radius to be constant. But for calculation here, I will promise for you to, if you start with the theta, for 90% of the time you will be fine, okay? Unless really your angle is not constant, okay? So this type of graphs that we have, usually the angles are numbers, okay? So as we know, we have to start with the constants. We have to start with the limits to be numbers, because at the end, your result must be a number, right? So because it's finding a value. So what's the limits of the theta? Just to remind you, the polar system start always from here. So the angle equals 0 is just the positive part of your x-axis. This is your angle equals 0. And it's just really like what you have learned in trig, is just rising or increasing in this direction. So that's just giving you the limits for the angles, right? You have started from the 0 and you go all the way to the pi. So that's it. This is your limits of integration for theta. Make sense?
Yeah.
And then next term is for the radius. So the radius is always pointing out from the origin. Start point for the radius is always the origin. The first thing that you hit before this shaded region is radius of the 1. The last link that you hit to finish that shaded area is just going to be 2. So your radius is changing from constant circle of 1 to the constant circle of 2. So radius will be constant, means you have 2 circles bounded between 2 circles. And then that extra factor of r, which is always sitting there, it has a name. We call it Jacobian. So this name is coming from changing variable, change variable from xy to r theta, called Jacobian. Okay. When we get to the 12.8, I'll tell you that that was always there for even for u substitution, but you didn't know that's Jacobian, okay? So then what was the integrand? So it was a square root. So this is just square root of 16 minus r squared. And then I just need to integrate this by just one u substitution, okay? So this is it. And I will say for this one was really tough if we don't transfer to the polar system because of trig substitution that we have to do. So for this, again, one more time, these are my u substitution thing that I really encourage you, please do it in your mind, please do it in your scratch paper. And then as much as you can just really save your time. So this is just what you're supposed to call your u. And what I'm writing in this color is just the one that you can do it in your mind, okay? You just need to practice. So then your derivative is going to be minus 2r dr. And then if this is just was originally square root of this 16 minus r square is your u. And then you have a du. And since that half is there, so you have to subtract, sorry, you have to divide by 2 because it does have r, it doesn't have negative 2r. So that gives you negative half outside. So then you have half plus 1 divided by half plus 1. and then you have negative half because of that constant to be outside. Okay, so if I do all of this step in my mind, so it means I should have integration from 0 to pi, and then I should have u, which is this, to the power of half plus 1 divide by half plus 1, and then that was just for integration of square roots. And then I have had one extra factor of negative half because of the derivative was negative to r. Okay, so that is just because the derivative was negative to r. And then I need to plug in the values of 1 and 2, and then do the integration of the next term, which is the d theta. Any question?
Just give me a sec to catch up on the note, because you do use substitutions a lot faster than I'm used to.
And then I'm encouraging you to do that colorful thing in your mind. Okay, so because we will have several of those that we can just practice, take care of the constant in derivative, put it outside, and do that square root thing inside to the power of half plus 1, and that's it. Okay.
What happens to that R, your Jacobian R?
Yeah, that was
Did that one get canceled?
no, this is your d, this is your du,
RDR.
this is your du, is your du. I need it for my du.
Oh, you pulled out your, okay.
Constant.
I see. Yeah.
Okay. Plug in the numbers, so then you will have integration from, I'm going to just leave it for integration for now because I have so many constant to factor out. So this is negative half, 1 half plus 1 is 2/3. And then I have 16 minus r square, which is 2 square to the power of 3 half. And then 16 minus 1 square to the power of 3 half. So these are all the constants you can factor out. And then I have integration from 0 to pi d theta left. Because so these are all constant, I just blew it out. That gives me 2 and 2 cancel out. So negative 1/3 left. That gives me 16 minus 4. And 16 minus 1 to the power of 3 half. And integration, this part is another integration. I want you to do it in your mind. So this is just really not necessary because it is integration of constant of 1, right? So it's integration of constant of 1, and that gives you really theta, right? So when you go from 0 to pi, so this is basically upper limit minus lower limit, right? Sims is just really integration from a to b of f of x, sorry, d of x. So it's just really end point minus the start point, okay? So that's the end point minus the start point, which added just 1 pi over here for us. Pi minus 0 is just pi. Does it make sense?
Where did that pi come? Like, what did we plug that pi into? Because I don't see any constants. I mean, any variables.
It's when you integrate d theta.
Oh,
get
just
theta.
the theta on its own. Okay, okay.
Yeah, and then you just plug in the upper and lower limits. I have a question. So when you change it from rectangular to polar coordinates, the setup for the integrals is not the same as the rectangular coordinates, right? So
No.
for rectangular coordinates, we usually have the constants on the outside integral, right?
Mm-hmm.
And then for polar coordinates is the opposite.
What do you mean by constant integral? You mean the limits of
The
integration
constant numbers,
is constant?
like from 1 to 2, you know, for rectangular coordinates, I mean rectangular coordinates, yeah, when we do the double integral, the numbers are usually on the outside integral.
Okay, which is here the same. 0 and pi are constants. Everywhere
Right,
is
so
the same. Okay.
right, so it doesn't change, so it's the same thing. Okay.
Yeah, that's what the yeah, exactly. But I need to remember always I must have the first integration limits constants.
Okay, got it.
Any other question? Any other question? Okay. So these are the steps for the same problem. So this is the next problem. Okay, so this is just the volume. This is finding the volume. Just to remind you, if you are finding the volume, that would be just double integration of a function of two variables and then dA. So if I want to translate it here, that would be just everything in terms of the polar, extra factor of r and dr d theta. But still, that's just is going to be your volume, right? So this is going to give you the volume of whatever you have, right? So I'm going to grab one more time right over here. And this is just, this one is just a paraboloid, but it's upside down. Okay, so this is going to be a paraboloid upside down. I know the radius is 1. How do I know? Because I just set the z value to be 0. That's xy plane. So z is 0. So that gives you x squared plus y squared equals 1. And that tells you this one has a radius equals 1. Okay, so this base one has a circle with the radius of the 1. And then I need to have always two graphs. One is to set the limits of integration. One is to find the integrand. So that was just the circle with the radius of the 1, which is my base, which gives me the limits of integration. And then, okay. And then the three-dimensional is just what's my roof, what's my integrand, okay? Ready? Okay. You have to set the limits of integration for angles first. Usually it's constant. I have started always 0 in trig in just unit circle is right over here. So to cover my entire shaded region, I have to go all the way. I have to go all the way to the 2 pi. Is that fine? Agree with this?
Yes.
And
Yeah.
then the next turn is for the radius. To cover the radius, I have to start always from the origin, and then I have to point it out to cover the shaded region. So point it out to cover the shaded region means starting from the zero radius, all the way to the 1 radius. And that is extra factor of r, which is the Jacobian for this changing variable. Since I'm finding the volume, now I do have the integrand. So what's my f of xy, which is finding the area under that surface? What is area under that surface? So this is my surface, right? I'm finding the area under this surface, which was originally, what was it? 1 minus r squared, is that true?
Yes.
That's it. So this is 1 minus r squared. I think the integration is fine, right?
Yeah.
It's super easy integration. Why? Because I don't have any theta. It's just really un integration. Is there any question about this one? Should I integrate?
Yeah.
Yes?
Yes.
this is distributing R inside, distributing R inside. So then R is just R squared divided by 2. R to the third is going to be R to the fourth divided by 4, plugging the value of 0 to 1. Next term is for the theta. So this 0 gives me all 0. So I'm just plugging the 1/2 minus 1/4. That's a constant, so I just factor it out, and then I have 0 to 2 pi, the angle of the theta. Again, that's a part that I said I don't want you to do the steps because it's basically endpoint minus the start point always, right? So then you have had this thing, which is 1/4, right? And then you have had the endpoint minus the start point, which is the 2 pi, okay? So this is the steps that is skipping right over here. And that would be just theta plug in from 0 to 2 pi, and that would be just only 2 pi. Okay, so endpoint minus the start point because there is nothing to integrate in terms of the theta. And that gives you pi over 2, and that's your answer. Any question? Move on?
Nope.
No.
Nope.
Okay. Fine. So this is same problem, same calculation. And that's just really reminded us, okay, if you do this problem by whatever we have learned in 12.2, that would be disaster, okay? So because in this case, as you see, the limits of integration was through that circle, which has the radius of the 1, and that is going to be from -1 to the 1. So this is from -1 to the 1 for the limits of x. And then for the limits of the y is going to be from negative piece to the positive piece. So you are going from here to here. So this is the limits which you have started from negative piece of the circle to the positive piece of the circle. And if you do it if you do it in this, what is it? Rectangular coordinate system, that gives you such a disintegral, which you must do trig substitution, and we don't like that one, okay? So that's just hard, that's why we prefer to do in polar. So this is another, I will say, nice example. It has many nice points here, like just setting the limits of integration, and it's just really first time that we have two z's in the problem. It was always one surface, now it's two surfaces. Still is finding the volume, So this is a good place to remind us, as we have had in the previous course, to find the area. So let me remind you, for the area thing we have had, it was just really y top graph minus y bottom graph, okay? So then you just get the area between two curves, which one of them is top or bigger, and the other one is bottom and just the smallest. So then you just have to get the area by always subtract the biggest one minus the smallest one if you were in previous course. And this course has to be the same thing if you have double integration. So you have one z or surface which is the bigger one, which is on top, and then you have one z which is the smaller one and is on the top, on bottom. So that's just going to be the volume, okay? So if you have two surfaces, you have always something is sitting on top you have always a surface which is sitting on top, and then you have another surface which is just really on the bottom of your surface. Okay, so that is something between these two, if you have to. For all of the problems that we tried by now, the bottom piece of your surface was 0. Let's just go back. Why I haven't had that issue over here? Because that is just your z top, which is whatever is your probability equation, and then this is your z bottom part piece, which is just xy plane, so it's 0. That's why when we have had z top minus z bottom, you didn't worry about the bottom piece because that was just really 0. Okay, and then that's the first example. As I said, I have two surfaces. One is top part of my solid, and the one is the bottom part. I have to subtract inside the integrand. Okay, and again, one more time, I'm going to just graph every single surface, right? So you have a first one, you have a sphere with the radius of 3. So the first one, it was a sphere with the radius of 3. The other one was the cone with the, which piece it says? It says find the volume of the solid above the cone. So if I just want to shade it, it's just really above the cone. It's above the cone, and it is below the sphere. So it's below the sphere. So it's just really this piece. Okay. So below the sphere and above the cone is going to be this part of the graph. So if it's that part, I'm going to erase the entire sphere, or I can keep it. No, I like to erase it, sorry. So that was the piece that I'm looking for. Okay, by what I have explained, the z top is the sphere, and that gives me 9 minus x squared minus y squared, and then the z bottom is just your cone, which is x squared plus y squared. Okay, I have actually this radius of 3 right over here to remind you. It seems the base, or what you need to set the limits of integration, is not the same as the 3. Do you see it's smaller than 3? Okay, so this is going to be the region of integration. Do we know what's the radius of that region of integration? Do you know what's the radius of that piece? Any idea?
It would be 0 to 2 pi.
It is 0 to 2 pi, yeah. But what's the radius?
What's R?
R, I guess.
No, constant.
Isn't
much?
well, I mean, your cone has it's the same diameter as your cone. So you'd have the same radius as the top of your cone. Right?
Mm-hmm.
Is it R minus the radius of the cone? Oh no.
Do I know what's the radius of the cone? It's the same as radius of the cone. But do I know what it is?
We know what the sphere is.
Okay.
No.
How do I
I
get
mean,
this one?
Well, I mean,
yeah.
you can. You can know if you do some math.
So, what's the math?
Hold on. If you take this part, make a triangle with it, then make this triangle, and you're trying to find. So let me erase my triangle.
Did I know? I didn't touch yours. Oh, okay. So when I maximize, I don't see yours.
Okay.
Anyone else is seeing what the? Let me just.
Let me write this on a piece of paper then.
Yeah, I can't see the annotation. I think I understand what you're talking about, though. You're setting a triangle at the base of the cone, the yellow circle that's on the bottom. You're setting a triangle from the origin out to your limit of integration, and finding the base of your triangle.
Side of your triangle.
So all you need to do to find it. Let me turn on video. And take off the sticker. Is you have this point, which is 0, 0. You want to find out this. What you can do is you can find out this point, and you can find out this point, and make a triangle with it, and then you can find out R.
Yeah.
Okay. So you know that what is hypotenuse of your triangle is exactly 3, because that's just the sphere, right? So because of the sphere, this piece, you know, is exactly 3, because it's just really the radius for one of the radius for a sphere. So that's exactly 3.
Oh yeah.
Okay.
Wait, say that one more time. The radius of your or the hypotenuse is 3 because of the radius of the sphere?
Yeah, because this is the radius of a sphere, right? So there was originally one sphere over here, right? It was just originally one sphere here, and that's just really from the center of the
to the edge of your sphere. You're right. Okay, I see it.
But what I'm doing right over here is just really set these two surfaces equal. That place is exactly intersection of the cone with the sphere. And if you set the surfaces equal, and then you solve it as you're supposed to have the equation of the what is circle, so that's your radius. Do you see what I have done?
Yeah.
Set the surfaces equal, so that piece is exactly intersection of your two surfaces of sphere and cone, and then set the z equal, so that gives you the intersection, which is exactly that radius I'm looking for, 3 over square root of 2. Does it make sense? Sylvia, Nora. Brandon is not here. I don't hear Brandon today.
Yeah, it makes sense.
Brandon, are you here?
Yeah, Brandon's here. He's in the. He was just muted.
Okay. Anyone else? Does it make sense by now? Anyone else? Okay.
I'm trying to process it. Do you mind going over it one more
The
time?
calculation, Danica?
The setup for it.
This let me just point it. So is it the entire graph or just this piece?
Just the graph. Like, how did you like visually see it again?
Oh yeah, that's a good point. Okay, so what I have had was just first of all, it was just a sphere. Okay, so then I have made that. I'm going to just erase it later, don't worry. Okay, so I just make this one over here. Okay. So that was a sphere, and then this is just the cone thing that I need to graph. So this is the cone, it goes like this, right? And it says it's supposed to be above the cone, and then it's supposed to be below that sphere. So then this is the piece, okay? But in order to see what's the limits of integration, it seems there should be a sun or light right over here. So this is my sun or light over here. So when I'm just seeing from the top, it makes the shadow, right? So that shadow of the graph gives me the region of integration always. Okay, so you have to imagine what would be the shadow. It is still a circle, but what's the radius of that circle? It's not entirely all the way to this 3, so it's smaller than 3. So then, since this point is really intersection of two surfaces that is given in this problem, so then you have to set the equations are these two surfaces equal. So that was one surface, which is the sphere, and the other one is just the cone. When I set them equal, that gives me the equation of the circle, which has the radius of 3 square root of 2. Does it make sense?
Okay, yeah. Thank you.
You're welcome. So limits of integration for the angle, for this type, what is it? 0,
Pi,
2 pi.
2 pi. Okay, so let's just show one more time with the arrow thing. I need to select a color that is clear in that yellow, huh? So which color do you think works? So this is just really equals 0 for angle, and then that's what happened for this circle. It has to be all the way to the end. So that's just really the angle which you set from 0 to 2 pi. And then I will do with the purple, say, how does it work here? So purple is showing you the radius to cover the entire or shaded region is going to be started from 0 and ending by whatever was the radius of the circle that you found. So that is the dr, and then you have r. Okay, so remember I said this has to be z top minus z bottom when you are finding the volume. So it's just always z top minus z bottom. And I made it what is my z top and z bottom over here. I just prefer to have a lighter one. So let me make it this type of blue. So this is my z top and this is my z bottom. So I just need to write it over here in terms of the r. Huh? Z top is 9 minus r square root minus the bottom is square root of r to the second, huh? So which is just really r. And that is r, and this is the r and the theta. Am I fine? Oh, sorry. Any question? Any question for this one? Move on. Yes. As far as integration, I will practice one more time that thing that I said. Please do it in your mind, okay? So please try to practice, do it as much as you can in your mind. You don't have to write the steps. So that was the u substitution, which is under the rad. So then your derivative is going to be minus 2r dr. So what I'm supposed to integrate is the square root of u du. Remember, I just need this r dr for du right over here, okay? So if not, I can't do that u substitution, okay? So this is for the piece of 9 minus r squared, 1 r out, and then dr. So this is going to be 1 negative half. So let me make some room here. So this is going to be 1 negative half outside because of the derivative. Okay, so this is negative half outside. This is half plus 1 divided by half plus 1. And that's just really what okay, sure. Give me a moment. If I can finish this one, I will give you the break, okay? So that would be the first piece, as we said, is 9 minus r squared to the power of 3 half divided by 3 half, and then this is just negative half, and plug in the values, whatever it is from 0 to 3 rad 2. And the second piece after this negative sign is just really 1r out of the radical notation, 1r multiply inside, this still is r squared. So that would be r cubed divided by 3, which you plug in 0 to 3 rad 2. Okay, I'm not worried about this part of integration is in terms of the theta, because there is nothing left in terms of the theta. It's all in terms of constants, right? So it was just really plug in the values and then get the values or constants after this step. What left is just really from this piece is another 2 pi, which I can just multiply by entire numbers that I got from here, okay? So let's just make the break, because let's just really plug in the numbers and they are not really nice numbers. So let's just really start the break if you want. I don't have time here. Okay, so it's right at 11:58 right now. So let's come back at 12:05, okay? Let's come back at 12:05, but still we are here, okay? So if you have any question, still we are here.
Yeah, I think we're all here. I am still here.
You can ask your questions if you have any.
What's the meaning of life?
I think it's
Right.
42.
My phone? Are you sure? My phone is ringing. I don't see anything.
No, it's just that during class it would go off every 15 minutes.
Oh.
Or the breaks. They're talking about the breaks.
Yeah, that's a good point. Yeah. You know, because again, when I'm teaching and especially because these type of problems are really long, I totally forgot about the time. Okay, so I really forget about the time. So I need another phone because I don't have any phone. You know, I need another phone because what I have right now, the camera, I feel students need to see the face when I'm teaching. Sometimes not. I don't know what you're feeling, but I kept the camera on my phone open for you guys if you want to see me when I'm talking. And then the other one is just using for iPad is using just for writing. So then I don't have any other device right here to set the time. But that one 15 minutes at least for timing helping me too, because I just when I was teaching I didn't know it's just really passing 1 hour. I thought it's really half an hour. And then Peter told me I need a long break.
The stretch break.
Yeah, stretch break. Yeah, I do need a stretch break. I'm going to do right now because I'm sitting for 1 hour like this.
So I went to the restroom. I don't know what happened to this guy over here.
She's just taking a stretch break. She'll be back in a second.
Yeah, do your stretch break at your place. I think at the end of this type of classes, my back will be completely bended. Always.
Is it Sylvia? You had a question about the integration part?
Yes.
Who has?
Because I don't know what happened to the minus r squared. Like that kind of seemed to disappear when we did the u substitution.
The u substitution, so the u substitution here, okay. The u substitution here is only for this piece, right?
That's legal?
What do you mean by legal?
I thought when you did u substitution, you were only supposed to do it for the entire thing.
Remember, the rule says if you have double integration of f plus g dA, you can take care of f dA plus take care of g dA. Right? So we split it out to two different pieces. And that's super, super legal. We can do it. So this is my f and this is my g. I've done it completely separately.
So there is another u sub for this one too. It's just not written. That's all.
No, it's not written. The second piece, the g piece, that doesn't have u substitution. It's just really r. Let me just make it different color. The second piece that I did not write it does not have any u substitution because it was just really one r left from here to another r distributed outside. So it's r squared. So then the result is r cubed divided by 3.
I think she means this.
I meant integration. I didn't mean u sub. I meant integration. Sorry.
Integration, yeah. So this is my second piece of integration.
Yeah, it's just not right.
It doesn't make sense. These colors, I think, make it more clear. These are all with one piece. These are all with one piece, the yellows, and the blues are the other piece. We take care of separately because of this rule right over here.
Should this part be all written like over here?
What is over here? I don't guess.
Like, it confuses me that this part is written like on this side. I mean,
use the color code to tell me what do you mean by this and this.
I'm drawing. Okay,
No, I don't see your draws. Sorry.
Oh, it's you know how the baby blue you've highlighted and wrote 2 pi underneath it?
Mm-hmm.
Should that be like way to the far left of the equation?
Yeah, so we did not multiply the 2 pi yet. Okay, so that 2 pi is just really all things that we got at the end. And then I'm just writing still multiply by 2 pi.
Okay.
Because I'm still plugging the values, and then this is just really cube. That's really ugly number. So 3 root 2 cube, and then 1/3 of the whole thing. Huh? Then whatever it is entirely multiply by 2 pi.
Okay.
I'm going to stop here. That's enough. That's enough simplification, huh? I don't see what is in chat room.
I kept it all in radical format because I was too lazy.
So that's fine. Sorry, I came here to just check your chat room because I don't see when it's maximized. What is in practice, Peter? The printer, huh? I scared to buy something like that. How about if it doesn't work? Whose bird is for? I think they put some sign on the phones. I don't think it's a real bird. Listen. Anyone has the real bird at home?
I don't.
Mm,
I have a cat.
I know. I mean, that was the first person in the class that we know him. Is it he or she?
It's a boy.
Yeah. Any question for me? Should I move on, guys? Okay.
Yeah, we can move on.
Yeah. So what was it? That's just really the process of doing the integration. As I said, this is a really nice example. And then it doesn't have the details in this PowerPoint. So that's why I just try to keep all the details over here. So the thing that I said, you might have type 1 or type 2, and then for most of the cases, or 90% of the cases, we start always with the theta. It's just right over here. It says, let me use the highlighter. So it says you might have this, what is it? R's are constants. So it looks like this when you have lines in your, sorry, theta is constant. So this is really two angles of constantly between alpha to beta. So that's how does it look like when they are constant. And then when you have this radius, if it was constant, it's supposed to be like this, right? So it's really a full circle. If it's a constant radius, it has to be a full circle. Since it's not a full circle, as you see, it is just really bounded between some two curvy shape, right? So this is just really bounded with some curvy shapes, which is still, we do the same thing. We are pointing out from the origin. whatever we hit first is just our what is lower limit, and then we end with the next line, and the ending shaded part is going to be the upper limit. But what I need to remember always is how theta is increasing, how r is increasing, okay? So if you are working with the theta, this is the 0, and then you are moving like this. The first thing that you hit, the last thing that you hit, because the theta is moving in this direction to increase, right? And if you are just doing the radius always starting from the origin, always is increasing in this way. So it's increasing in this way. So then if you know, these are going to give you the dr, the limits of the r, and then that's angles way of what was in unit circle is going to be the what is it, the d theta. Then it's just really same process always. Okay, so let me erase the extra circles. Okay, so if I'm looking for the angles limits, I go and make this type of arrows, because that's how the angles are increasing. And if I'm just making the radius limits, so I just moving in the radius increasing, always pointing out, starting from the origin, and then see which line or curve we hit first and which line or curve we hit last to set the limits of integration. So again, we don't call them type 1, type 2, but it's really similar to that one. So this one, the angles is constant, and then the r is not, it's between two functions. And then we don't have really most of the cases in this course, but we might have the other way. We might have the radius is between, I don't want to write it because it's not really the case that you see. If you have radius between two constant, and then the angle is curvy shape, so then in this case, that's is r equals a to r equals b numbers, and then this from this curvy to this curvy is functions, which again we don't have it in this course, this type of region, which is type 2 region. We have always type 1 region, which is right over here. We have done it. Okay, and I'm going, because I wrote it over here, and later you might see this one. I want to complete it. That means this is first, and then this is next. Okay, so we don't have type 2 in this course. Is all we have is type 1, the one that we have practiced. Okay, again, if you remember in calculus 1, we've seen this, sorry, calculus 2, this is calculus 2. We've seen this formula in calculus 2. Area in polar. This is area in polar, and it says it's just really formula that we've seen it in chapter 10 of our calculus 2. But I don't need to remember those formula, because now I know what is the double integration. Okay, so now because I know what's the double integration, when I see the problems, it says get the area by this limits, get the area by this limits. I will say, okay, so I supposed to have two lines for the alpha to the beta. So this is two lines. And then when I'm starting for the region, it says starting from zero to the some curve, which is h of theta. So this is just really some curve. So I'm going to shade this region, and the goal is find the area of this one. And then I don't need to know what I've learned in calculus 2, because this is basically means set the limits of integration of this double integral. So which gives you limits from alpha to beta for the angle, and then the radius is starting, as I said, always from origin all the way to the end. So that is going to be from 0 to the h of theta. Oops, sorry. Extra parentheses. And then that's just r, and whatever the function was inside for here, the function should not be anything except the 1, because we are finding the area, and that's it. This is finding the area. Then it's really matching with what we have learned in previous course, but we don't need to know, right? So because the previous course was taking care of one inside integration, which is here in terms of the r, which gives you r squared divided by 2, plug in the value, and that was the single version, what is integral version that we've seen it in previous course. So as an example, again, this is one thing that we've seen it in previous course. It says find the area for the r equals 2 cosine theta. So find the area for r, so it's just really without calculus 2. By whatever we have learned in this course, find the area for this one. This type of graph is what I don't expect you to remember from calculus 2. If you don't remember, it's just really using your calculator to graph it, or somehow will give you the graph. If it's just really the way that we have done this test, I'm not sure what I'm going to do for next test. I might use the Zoom to do the next test, not take home test. It depends on the next test, okay? But if, however it is, this type of graph is just what I will provide for you, okay? So if you haven't, because there are many teachers, they don't teach the last chapter for so many reasons. So the students don't know how to graph this one. So the graph of that one is what I need to provide if I give you this. So nothing else, okay? This type of graph, because it's just based on your previous course and is last piece, some teachers doesn't cover. So this is the graph of that, what we call r equals cosine of 2 theta. The question asks us to find the area of one leaf. Oh, sorry, let me read one more problem. Is it one leaf or 4? So use the double integral to find the area of enclosed one loop of these 4 leaves. One loop, okay, so that's the area. Okay. Ready? Are you ready?
Yes, I'm ready.
Okay, so then I have to say area is double integration of 1 dA. Okay, so limits of integration for the angle, as we see right over here. So again, this is going to be 0, but is moving from here to here, right? So this says it is from negative pi over 4 to the pi over 4. And again, because the graph is provided, okay? And then the r is always pointing from the origin all the way to the end point, right? Is starting at the 0, but stopping at that curve equation, which is cosine of 2 theta. So starting from the origin to the cosine of 2 theta. And then that extra factor of r because of the polar, there is no integrand because it's the area. And that's it. Okay, fine. I am going to integrate the middle, which is just r, which is going to be r squared divided by 2 from 0 to cosine of 2 pi. And that is this 10. I can't do what I've done by now because I do have something to integrate in terms of the theta. When I plug in cosine, that gives me cosine square divided by 2, and then 0 is just 0, okay? And this is what is the next 10, right? I have to integrate cosine square. So I will remind you, if we have in calculus 2, if we have even power of sine and cosine, we must use double angle formula. So what was the double angle formula? I have 1 plus cosine 2 times divided by 2. If it was sine, it is 1 minus cosine 2 times divided by 2. Just to complete here, if it was odd power of the sine and cosine, that's a must, because if you don't, you never end the integration, right? So I have to use this Pythagorean theorem for that case, okay? So this is the reminding you for integration, because that is half of whatever cosine square, right? So cosine square has to be 1 plus cosine of twice. So remember, this is already 2 times. This is already 2 times. I need 2 more because it's twice of whatever is inside. Does it make sense? And then I need to integrate. Okay, half is there. I just factor another half. It makes it 1/4. Integration of this is theta. Integration of cosine is sine. Divide by the constant. And then I have to plug in negative 4 pi to the pi over 4. I will say this is my first example. I have had something to integrate in terms of theta. It was always nothing. This piece will be exactly always for the values of pi over 4 times 4, which is pi. So it's 0, right? If I plug in pi over 4 is sine of pi. Sine of pi is 0. So I don't want to worry about that piece. So it's just really plug in pi over 4 to the theta upper limit minus lower limit, which is give you pi over 2, which is total of pi over 4. And that's area. Any question here? Any question here?
What happened to the one that was like my one, the one before the after the
Integration of 1 d theta is theta.
oh, you separated them. Okay,
It is E is a theta.
thank you.
Any other question? Move on. Okay.
Yeah, I think on the last step you made the 1/4 into a half.
Oh yeah. Thank you. That's 1/8. Thank you. Okay. So this is a nice problem too. This is just the last problem of this section. Then we can move to the new section. So this is my last problem of this section. Again, it's a nice problem because we have 2 surfaces. When we have 2 surfaces, the intersections are just challenging, and we have to, it's not as straightforward. We have to find it, okay? So what it says again, find the volume. And then it says these things, it has to be under the paraboloid. So if this is just really 3-dimensional graph under the paraboloid, I need a darker one. So if it's under the paraboloid, so it's right there. And it says it has to be above. Above means just really cutting on XY plane. Cutting on XY plane doesn't go all the way to infinity. And then the inside the cylinder. So this is my cylinder, so it's inside my cylinder, okay? So it's inside my cylinder. So what the volume is just really this shaded region. So we are finding the volume of this shaded region. This is a nice problem because it's the first time that we see what is circle is not centered at the origin. The circle is not centered at the origin, okay? So again, I'm going to graph it from the blank one more time, just to get the intersection nicely. So the 3D graph, I don't think helps me to get the limits of integration. So what was over here? It's just x squared plus y squared equals 2x, which I have to complete the square to get the complete the square means what? Complete the square means make this value half and then a square and then add it both sides. So when I'm adding one both sides, it's just really the process of completing the square to give me the center of this thing. So you have x minus 1 to the second, then you have y squared, and then you have 1, right? So that tells you where is the center. Center is at 1, 0, and then the radius is 1, right? So this is 1, 0. This is just the radius 1. Okay, so this is just 1, 0, and then it goes 1. So actually I can just make this one right now on the 2-dimensional because that's what I really need for this is going to be x, this is going to be y, this is 1, and that's radius 1, so it's just 2. Okay, so that's just really base of my graph. That's where I need to set the limits of integration. Okay, on the next graph was the paraboloid. I'm going to make the paraboloid exactly right over here. Okay, and as we said, we are looking for the area, something lighter. So we are looking for the volume of this piece. If I just want to call z top was x squared plus y squared, which is the paraboloid. If I want to call z bottom was just xy plane. Okay, so your volume is double integration of z top minus z bot dA, and set the limits of integration is this thing. Okay, give me my limits for theta. Just again one more time to remind you, this is the still theta equals 0. This is theta equals 0. This is the limits of theta. What it is?
Negative pi over 2 to pi over 2.
And then the next term is just the dr. The next term is just the dr. So dr starting always from the origin. What's the limits? That was originally x squared plus y squared equals 2x, but I need it in polar. X squared plus y squared in polar is r squared. X in polar is r cosine. So if I divide both sides by r, so that gives you polar form or equation of that circle. Now, can you tell me what's the limits for r? Starting at 0, ending at?
2 cosine theta.
Okay, and that's it, right? Your z top is just the paraboloid. The z top is right over here, is the paraboloid, minus the z bottom is nothing, right? It's just really XY plane. The base or the lower part of your surface is just really your XY plane, and that's it.
The lower part of our surface isn't the circle?
But what's the Z value of that circle? Is standing at the height of 0.
Right, we don't have one.
So that's it. You integrate it, okay? I don't think I need to do all the integration. What do you think? So this is going to be r to the cube, right? So integration is r4 divided by 4, which you go from 0 to 2 cosine of theta. Okay. So that is a big power, right? So 2 to the 4, and then I have cosine to the 4 of theta. And that's just really simplification. 16 divided by 4 is 4. And then I have to follow the same rule that I reminded. That's even power. When we have even power, we have to go by 1 plus cosine half angle formula. Cosine square to the second. And then you square that thing. First square plus twice of first to the second plus second one square. And then 2 square is another 4. I just factor it out. Then one more time. Use the half angle formula. 1 is 1. 2 cosine plus cosine square is 1 plus cosine. It's 2 already, times 2 is 4. And now I'm ready to integrate. This is based on our chapter, first chapter of calculus 2. Okay, all of these steps for this thing that I wrote is just right over here, okay? So every single details of the integration, and I've done actually by this step in that thing, it's just really one more step to integrate, and that's just right over here. You have them with the details here. Is there any question? Let me go back to where did I stop? Is there any question here? Question?
I don't quite understand. Oh, wait, never mind. Never mind, I got it. I missed an R.
You missed probably this R, huh?
Yep.
Any other question? Okay. This is it. I'm going to start 12.5, but that's just a really short introduction. What is a triple integration is really copy paste of whatever we have done by now. We go only one more step because obviously we have the third term, right? So we take care of X, we take care of Y, and then we take care of Z too. But the process are going to be exactly the same thing, okay? So process of the triple integration is going to be exactly the same because is basically do X, Y, and Z at the same time, okay? So for doing the triple integration, it's like any other type of integration. Why is blank? do you know? Okay, give me a moment, then you can rest right now. I think I know what's the problem. Usually it takes time. Okay. Is there any question for me?
If we're doing triple integrals, does that mean that we're going to go into the fourth dimension?
Exactly. So if the single integral is giving me what is the area under the curve, then the double integral is going to give me what is the volume under the surface. So then the triple integration is going to be what is hypervolume in fourth dimension under the three-dimensional surface. Is it normal to take this much time, guys? Steven, you have many experience of this.
Sometimes it can. I'm not sure exactly how or why it's taking a long time. How many slides do we have? Are there a lot?
It's a four-dimensional problem.
Yeah, there's 48 slides, so I think it's just
That's
having
fine.
trouble taking the time adding it.
Or maybe it's just shy.
Yeah, it's trying to perform with a class sitting here watching it that doesn't want to insert, and
Here we go.
it's scared.
Here we go.
There you go. Just needed encouragement, that's all.
Okay. So this is 12.5. And as I said, and actually as Sylvia asked me what we are planning to do, it was just really what we have done in previous course, get the area under the curve. And then in the previous section, it was get the volume under the surface. So now it's just really doing same thing with one more dimension, which is triple integration of a three variables function. So what would be this notation is just really volume. So this is the length, x is the length, area is subpieces here, and then in three dimensional, so the volume will be subpieces, okay? But the process of defining the integration is going to be exactly the same thing. We don't spend that much time on that Riemann sum thing because we don't have any problem on based on the Riemann sum. What we have is just really integrating by table of formula. So what it is over here, it's just reminding us there are 3 dimensions of x's, y's, and then z's. There are 4 now constants, so it's making a box. So this is making a 3-dimensional box. If I start to chop it in all the dimensions of x and y and y, so this is x and then y and then z, so the sub pieces is going to be cube shape. So your sub pieces is just going to be cube shape. That is just 3-dimensional sub pieces. So again, in 1-dimensional single integral was the length, delta x only. 2-dimensional, which was previous 12.2 and 3, that was delta A, so it was area. Now I have 1 more dimension for my sub pieces. So they are making cubes or little boxes, and that was just really 3 dimensions of x and then y and then z. So which the product of them is giving me the volume. So now the sub pieces are the volume, not the area anymore. And then in just really same process that we have done any integration by now, chop it to the pieces, pick a lucky point, and then make a Riemann sum, then you have a new type of integration. So make a Riemann sum, it has to be triples because it has x, it has y, and it has z. So you make the Riemann sum, and that's just really what we call triple integration. So again, conceptually, we just have somewhere in our hyper dimensions. So hyper dimensions, which is for now 4th dimensions, but we don't need to worry about that one. It's just really evaluation that we just take care here. So this thing now is dv. Why? Because it's just sub boxes, just the volume of sub boxes or little thing that we have it in x, y, and z direction. And that's just really what's happening, right? So you have to take care of your order. So are you going to do first dx, then dy, then dz, or you can do any other order, right? So there are really, how many orders do you know? There are 3 of them. If you put it's not repeated, right? So if you have learned
Is there
permute,
9?
so if you have learned no, one more try. So to
6 different combinations?
Yeah, it's combination, yeah. So to select the first one, it could be either dx, dy, or dz. Since already you take care of one of them was either dx, dy, dz. So then 2 left to select the next. And then when you take care of 2 of them, so 1 left to just get the selection of the last one. So you have 6 possible order of integration. So you have 6 possible order of integration, and that means you can do again whatever is easier first. We used to see dx, dy, dz, or we just say we used to see dx, dy together and then dz either first or last, but that doesn't mean it's just really the best way. It's just really whatever is easier to do. For most of the problem, we used to see the same way it is, right? So we take care of xy first, so dx, dy first, and then we take care of the z next. So that's just really for most of the problem. But as I said, there are 6 other possibilities which I will try for some problems to see they are really similar, okay? So what does it mean? It's just really partial integration one more time, right? So when you have started from this inside one and you are taking care of the dx, so means partially integrating in terms of dx. So obviously your y and z are constants, right? So partial integration in terms of x, y and z are constant. So then if you go to the next term, and that's just really partial integration in terms of the y, so then your z is a constant because it's not term for the z, okay? So that's really partially integration. What we have done in the partial derivative is exactly the same way, okay? So this is what is explaining here, but it's just really easier to go with the numbers, right? With the problems. So as I said, there are 5 other possibilities. One is listed there, so it's 6 total. So all of them are equal. Why they are equal? Because Fubini's theorem, right? So we have had the Fubini's theorem before. Fubini's theorem, it says you are okay to change the order of integration if you feel is easier, right? So that's just the permission for us, Fubini's theorem, to change the order of integration. As you see, the problem is giving you dv, so means is on your hand. Whatever order you prefer, start to do it, okay? Which order do you prefer?
The easiest one.
Since they are all constants, they are all easy. So let's go with this. What x first? So this is x. If you do x first, your limits of x is right over here. So it's from 0 to 1. The next term is the y. So limits of the y is right over here from -1 to 2. That is given. And then the dz is right over here from 0 to 3. Okay. So then we keep the outers as it is, and as usual we have to go by order of operation or inside is first, right? So if I take care of the inside, what is the y constant, the z constant? So this is just integration of x dx. So you are doing the integration of x dx while y and z, both of them are constant. So that gives me x squared divided by 2, and then plug in the values for the dx, which was from 0 to 1. So still dy left, still dz left, right? So you take care of your inner one, which is dx, but the outers left. And actually they are constant. So whatever it is, if you plug in, it gives you a constant. So I'm just going to factor my constant out. So this is going to be yz squared then dy dz, okay? So then you have to take care of the next term, which is going to be the y. When we do the y, so the z is constant, huh? So when you do the y, the v is constant, so that gives you from 0 to 3 of the dz, and the y is constant. Sorry, the z is a constant, okay? So I keep the z square because that's a constant. I need to integrate only from the y and then dy. So y and dy, that gives you y squared divided by 2 from -1 to the 2, okay? So again, that's a constant, right? So if I plug in y to be 2, so it's 2 squared divided by 2. If I plug in y to be -1 squared divided by 2, that's a constant. So I just factor it out. All left is just really 1z squared dz. So that gives you 1/2. That was 4 divided by 2 minus half. And that is the last term, which is z squared. Integration is cube divided by 3. Plug in the value of 0 and 3. So this is 4 minus 1 is 3/2. So it's 3/4. And that is another 1/3. And actually it's not 1/3, it's 27, right? Because if you're plugging 3, cube is 27. So the answer is 27 divided by 4. Can you follow the steps? Is it fine? Everyone can follow. The third one is really similar process of partial differentiation, right? So when we have 3 variables, if you partially integrate with respect to the x, the other 2 must be constant. Let's try nothing, right? Because it's time.
Yeah, just about.
Okay. So the triple integration again has nothing new. We can just do it without any lecture. All I need to do is just whatever we have done in partial integration, we can do it. But it doesn't mean I don't do examples. So that's just a good point. We have started then we can review at the beginning of next class. When we review triple integration, it seems we will review the other things too, right? So we will review the double integration, because at the same time we have to take care of double integral inside and then go to the triple integration, which is the outside one. So is there any question for me? If it's not about the triple integration, can I stop recording?